Hello everyone, before we start, I'll recommend you guys to watch these videos first. If you're done, let's get into it. Here, we recall the force F capital factor for continuum body in region omega is about this integral, which by Einstein notation equivalent to this another integral, which for second term in the first equality and the second and third term for the equivalent integral here, the Leibniz rule stay the same, which Leibniz rule here for nabla operator or in general as covariant derivative in previous video. By taking dot product like this will equivalent to this integral, which this dot product relate to generalized dot product or inner product. So the right hand side integral will be in index notation just like this. That's about the kinematic. But the question is, what inside F factor in previous video besides only gradient of hydrostatic pressure? In previous video, we know that the integrand here will equals to F mu, which F mu is equals to this, and the F bar here we can decompose as F bar internal and external. The external part here relate to gravitational force, electromagnetic, and etc. But here, another equation incoming. What inside F bar internal? And the answer is because the F bar internal relate to characteristic of our continuum body system, so then it relate to deviatoric stress, deformation, shear, and etc. But how we model at least these three? Notice that F bar internal here depend on pace. Pace is about is it fluid or is it elastic body, which the left hand side of this equation is in interpretation as Eulerian that only simple to analyze the fluid. So here there is another view as Lagrange simplified elastic body model, which in this Lagrange position of x is equals to x capital as initial position plus some kind of displacement as chi that depend on x capital and time. So the velocity vector equivalent to this v mu component that is equals to the first partial derivative of chi with respect to time. So here, the main difference between Euler and Lagrange is about, in Euler, we have total derivative as we know in previous video, but in Lagrange, we transform the total derivative as partial derivative because we know explicitly velocity depend on t and x capital that independent of time. And then the first basic. The next basic here, suppose we have a system, there is a container which the floor is yellow and the fluid or at least the continuum body is about blue in very wide container. Let's say in this point it has velocity vector as this. So we model that by friction between floor and continuum body, the velocity at ground level here is equals to zero vector. So if we take step higher, let's say h, we get the velocity is equals to velocity 1 vector, which with the same direction greater than zero vector. Then we take higher and higher level of continuum body, so we get a v vector, what we place first, which is equals to max level of continuum body that we know is greater than v1 vector before. So by this illustration, we can see that v vector differ locally along some direction that may take different path from its velocity. So here, F bar internal mu proportional to covariant derivative mu to velocity nu that we can decompose as this, which known as tensor symmetric and antisymmetric decomposition. By this proportionality, we can characterize especially viscous fluid. Next, we assume that in our continuum body, there is no intrinsic angular momentum. So by this assumption, angular momentum, which we can define as this, that analogous to momentum, if we take the first derivative, it will create torque that equals to this. Notice that x nu can go inside to the differentiation because the first total derivative of x nu is equals to v nu that is perpendicular to v nu itself. So by Levi-Civita symbol, it equals to 0. So we can rewrite the integral as this, which for dynamic part, we have Levi-Civita and then the x and then gradient of hydrostatic pressure plus F bar internal, such this is first rank tensor, so the proportionality relate to second rank tensor and need to be contracted. By contraction with, let's say, by covariant derivative here, and defining inside of covariant derivative as sigma mu nu, so then we get that second term of dynamic integral is about this. And the next section, we will focus on second term. By product rule or Leibniz rule, we can get by covariant derivative as this, which in this second term is about anti-symmetric contribution of sigma. And you will see that first term here, we can rewrite as this, which is by this form, we can get the integration of it as boundary in region omega after integration. By angular momentum law that we get the form from this property, which the next consequence by dynamic part, sigma and x will be like this equality, so we can have conclusion that sigma is a symmetric second rank tensor. And the next important property, sigma only explain about deformation dynamic. So the contribution of sigma clearly only it reshaped, not by zooming or just like that. So trace part or contraction between the two index of sigma is equals to 0. Actually, there is a lot of model about sigma. So we take example as linear stress theory. Sigma or stress tensor, in this theory, we can write as this, which the last part is about contraction or trace part. So to normalize this mu constant, we add 3 for 3 dimension. And notice that the first term inside the bracket here is about shear and the total of all is about stress. Or to be precise, deviatoric stress or reshaping stress. And we must be clear that this model only works in fluid case. So by elastic body case, we have the same pattern as this, or we can see that both in elastic body and fluid case, there has analog to the stress tensor. For fluid case, we know this in model as Navier-Stokes, and for all the stress here, has assumption that satisfy Cauchy theorem, later known as Cauchy stress. So by summary, we have F mu for dynamics is about this, and by analog we have this for elasticity in elastic body, such P here in Navier-Stokes is about hydrostatic plus thermodynamic pressure. In elasticity, the P here only explain about thermodynamic pressure. And we must note that this is linear theory, but in many cases it being standard. So this linear theory in the nowadays research being standard model that linearized most of complicated system. And that's the introduction of Cauchy stress tensor and many things. I hope you guys enjoy this video. If you like this video, don't forget to share and subscribe. If you guys have any questions, please drop comment below. And that's it. See you later.